for joining, and welcome to the second lecture of the day. And it's my pleasure to introduce Ilaria Castellano. I hope I pronounced it well. She's going to talk about introduction to totally disconnected local compact groups.
Thank you, Raquel. Thank you, all of you, for showing interest in my lectures. Here you can see the first page of the notes that I shared with you online, because just before I start with the lecture, I would like to talk about the plan for the week. So this week, there will be 3 lectures about this class of groups. And as you can see, there are 4 main chapters in the notes. This means that actually I will not talk about the last one. Probably I'm going to comment on this part today, but the lectures will be devoted to explain chapter 2, 3, and 4. Today is going to be a gentle lecture. So it's a warming up, as it's written here. I will talk about some preliminaries on topological groups that we are going to use further on. And the goal is to reach the definition of totally disconnected locally compact groups. And that's it. So probably you are already familiar with most of the things I'm going to talk about, but since I do not know your background, I prefer to have everyone on board with me in order to be then able to reach the substantial parts of the lectures, with the same knowledge. Okay, so let's start with this warming up. Let me change the screen. Okay, okay, let's go together. So a topological group is a group G, which is a Hausdorff topological space, such that the multiplication and inversion are both continuous maps. So here let me see. So here there is one assumption, which is the Hausdorffness of the topological space, which is actually not required for the definition of topological group in general. But during these lectures, I'm going to assume this hypothesis, and I'm going to show you that this assumption is not so big. So actually it's not changing the cards we are playing with. When I talk about multiplication, here you can see this product. So I mean that this product has the product topology on it. So this map is continuous when we consider the product endowed with the product topology. What this definition means that a topological group has an algebraic structure and a topological structure, and these 2 structures has to live together in peace. So we ask that the algebra on the group the algebraic structure is going to be compatible with the topology. So this is what we need. Okay, this is a topological group. The additive notation will be used only for abelian topological groups. So I'm going to use the multiplicative one for arbitrary topological groups. Let's see some examples. The first one, so the easy one, discrete groups. What do I mean by discrete groups? I mean that whenever you pick a group that can be your favorite group, any group you can think about, you just pick this group and then you choose to endow the space with a discrete topology. Since the topology is discrete, then with no difficulty at all, you can just check that multiplication and inversion are going to be automatically continuous. So any group can be regarded as a topological group whenever you endow it with a discrete topology. And we will refer to this kind of groups as discrete groups. Then we have the reals. The reals, anyone knows this group. This is an abelian group, and you have the standard topology on R coming from the Euclidean metric. And with this topology, this group is topological, so the addition is continuous. And then inside R, you can look at some subgroups, for example, Z and Q, or you can look at some quotient group, and you still discover that these are topological group again. But this is true in general. So there is this remark here. Whenever you pick a subgroup with a subspace topology, then you got a topological group. And the same is true whenever you quotient by some normal subgroup and you endow the quotient with a quotient topology. Then what you get is still a topological group. An important fact that we need about these objects is the following. So translations by elements of the group, no matter if they are on the left or on the right, and conjugations, these maps are continuous and open. And this property is quite easy to check. It's an invitation to check it. It's a good exercise. And it's quite important because if you work with topological group, you often use this fact. And yeah, it's something that is important to know. A consequence is that a topological group is homogeneous. What does it mean? This means that if you look at a point in your group and you look what is happening around this point, topologically speaking, then what is happening there is exactly the same of what is happening on some other point in your group. So each point has the same topological behavior. The neighborhood has the same behavior. So actually it is enough to know what is happening in one point and you know what is happening all around the group. But since the group has a distinguished element, which is the identity, for us, the focus will be looking at what is happening around the identity. So we will always care about the neighborhood of the identity element. And here, what I wrote is the following. So if you consider this set, which we suppose to be a neighborhood basis at the identity, and you translate this set, then what you get is still a neighborhood basis, but now at the point G. So this is what I meant before. You just need to know what is happening around the identity, and by translations, you can just see what is happening around any other point of the group. Okay, so if everyone is happy with these first few notions that are quite easy, I would like to do an exercise with you, which is, in my opinion, exercise 0 when you study topological groups. It is very easy, but I need to write something, so let's do this exercise together. Okay, I want to prove that if I consider a topological group G and and a subgroup H in G, which is open, then H is also closed. In order to prove this, I have to prove, so H is closed if and only if the complement is open. So this is what I want to prove. In order to prove that the complement is open, I look at G and I write G as disjoint union of cosets of H, where G is running in R, and R is a transversal. And we suppose, because I'm lazy, that 1G is in R. So since H is a subgroup, we can write G as a union, a disjoint union of left cosets of H. This implies that G, the complement, is the union of all these cosets, but G has to be different from the identity. So we are just taking H out of this union. And now we apply the fact that I just mentioned. So all these cosets are open because H was open and translations are open maps. So GH is still open. So the complement is union of open sets. So this is open and this is the exercise. In the notes, you can find some other exercises. Hopefully they are all correct, the statement they are all correct. And you can try to prove them. And many times you will use some trick like this. You will try to cover your set with some translation and translated subsets. And so this is a trick that often we use if we deal with topological groups. Okay. Let's see an example of topological group, which is not so trivial as the one that I made before. And moreover, this example is going to come back on the next lecture. So I really need it. And in order to introduce it, I need some terminology about graphs. Okay. A graph gamma consists of a set, V gamma, whose elements are called vertices, and the set E gamma, whose elements are called edges. And the elements of E gamma are unordered pairs. So this is, the order here is not important. So these are unordered pairs of vertices. So again, a graph consists of two sets. One is V gamma and the other one is E gamma. The elements of V gamma are called vertices, and the elements of E gamma are called edges. You can find in the literature several definitions of graphs. This one is, it's a simplified one, but it's good for our purposes. Here you can see a few examples of graphs, finite. In this situation, they are all finite. But we are going to talk about infinite graphs as well. So we have gamma naught, which is just a bunch of vertices. So actually the set of edges is empty. You can have something like gamma 1, which is a straight line connected to vertices. Or we can have a line which is closed, so a circuit, or a star, for example. So you have one vertex, and then this vertex is connected by an edge to all other vertices in the graph. So this is a good way to picture a graph, because whenever I have a pair BW in the set of edges, I just draw this edge. And this is how a graph looks like. If two vertices V and gamma form an edge, then we say that they are adjacent. A path from V to W is a sequence of vertices such that the first vertex is equal to V, the last vertex is equal to W, and then I also need the consecutive vertices. They have to form an edge. So a path looks like something like gamma 1 here, it looks like a line, but also a circuit can be a path, or also a combination of the two. So I can have a line and then I can have some circuit somewhere. Here I've written that I have this path from V to W, but I've also said that edges has no direction. So this is not an ordered pair. So there is no direction from V to W. So actually what I mean is that whenever you have a path in this unordered graph, actually you can move from V to W and from W to V, and we don't care about the direction you're using. The important thing is that there is a path. Indeed, most of the time we will care about connected graph. A graph is said to be connected if for any pair of distinct vertices, there is always a path connecting V and W. So there is always a way to move on the graph starting from one point, and you want to reach another point in the graph, you have always a path that is allowing you to do that. So this is what I mean by connected graph. Okay, so once we have a connected graph, or once we have a graph, because for the definition of automorphism, we don't need connectedness. What is an automorphism of a graph? It is what you expect to be. It is a bijection on the set of vertices, such that the bijection has to preserve the adjacency relation. So phi V, phi W form an edge if and only if V and W were already an edge in gamma. So you don't move vertices around, breaking the structure of the graph that you had since the beginning. So you have to keep edges in some sense in their position. You move edges around together with vertices. The set of all automorphism of gamma is a group under composition because it's a subgroup of the group of permutation of vertices. And we denote this group by auth of gamma. Here you can see that there is another exercise for you. This graph gamma is called a by infinite line. It's quite intuitive why this is the name of this graph. And I'm asking you to, let's say, classify, or at least to have clear in your mind what can be all possible automorphisms of this graph. So for example, you could fix one vertex and then flip the graph fixing this vertex, but there are other choices that you can do. And let me say that there are a few elementary moves that you can do, and then all possible automorphisms are going to be a combination of these elementary moves. So just think about it. It's something not so difficult. Okay, so now we have a group, but we are talking about topological groups, so we need a topology on auth of gamma. How do we define this topology? We choose finite sequences of vertices, V and W, and then we define this set, sigma VW. Sigma VW is the set of all automorphism phi, such that phi maps Vi in Wi for any, okay, this I here actually is equal to 1. So for any index, for every index, I have Vi is mapped to Wi. It's not difficult to check that the collection of all possible sigma VW, where V and W run among all finite sequences of vertices, it's not difficult to prove that this collection satisfies all the axioms for being a topological, a basis of a topology. So actually, this collection defines a topology that I'm going to call tau on the automorphism of gamma. But what do we need to prove is that this topology actually is compatible with the algebraic structure of auth of gamma. This means that we have to prove that composition and inversion are continuous map. So this is what I mean when I write here group topology. So whenever I use this term means that the topology I have on the group, if I look at the group as a space, has to be compatible with multiplication and inversion. So actually it is defining a topological group, because of course you can have different topologies on the same space, but at the same time they can be, they cannot give you a group, a topological group. Then the second part of the exercise is this one. So V gamma is a set. So we can consider V gamma endowed with a discrete topology. And the set of all automorphism of the graph is a subset, is a subspace of the space of all permutation of V gamma. So it's quite natural to try to endow this space with a compact open topology. So what I'm asking you to prove, or you should convince yourself that the topology I just defined actually coincides with a compact open topology one can define on out of gamma. Okay, let's see if as I said before, most of the time we care about what is happening around the identity, because we have now a topological group. So if I want to have a complete idea of my topology, it's enough to look at the identity. So let's see what is happening around the identity. So when the identity automorphism on gamma belongs to some open sets of the basis. It's clear that this is true by the definition of this set. So we have that the identity of Vi has to be equal to Wi for any I, but this is Vi. This means that V has to coincide with W. In other words, I have that the set sigma V, which is the set of all phi in out of gamma, such that phi of V is equal to V for all V in V. This is a neighborhood of the identity, and if I let these neighborhoods run over all possible finite subsets of vertices, I get a neighborhood basis at the identity in gamma. So this means that an automorphism phi is close to the identity if this automorphism stabilizes a large number of vertices. And larger, so and you are closer, as you're closer to the identity as much as is larger the number of vertices that you stabilize. And if you use translation and you move to any other, no, it's not G, but to any other psi in the automorphism group of gamma, the basis that you get is, so this is psi, this is psi B. This is the set of all phi in out of gamma, such that phi of V is equal to psi of V for all V in V. And V is again in V gamma finite. So for any other point in the group, this is a neighborhood basis. And so this means that two automorphisms are closed in this topology if they agree on a large number of vertices. Okay, so this is what this topology is telling us. Okay, there is an exercise here that allows me to do a remark, actually, because now we have seen how it is possible to define a topology on a group so in such a way the group becomes a topological group if you are lucky. But how can we sure that the topology that we have now is non-discrete? There is no, so in the way I have presented this topology, it's not clear if this is discrete or not. And actually the answer is that this is a very difficult problem. So usually it's a hard problem to answer the question, is this topology discrete or not? And also in the case of automorphism of connected graph, it's not clear if there is some kind of technique that allows you to understand if the compact open topology is discrete or not in the end. This strictly depends on the graph that you have. So this is why I've written here this exercise, because for the bi-infinite line that I drew before, if you look at the neighborhood of the identity, you should be able to understand whether the automorphism is the automorphism group is discrete or not. And then I want to also to once you have the answer for this exercise, a good thing to do should be trying to generalize this to something different, or not generalize because probably the answer is going to be different, but to try to go a little bit further. What I mean is the following. So the bi-infinite line that I got before has a few properties that are quite nice and that I'm going to list. So gamma has no circuits, so there are no closed paths here. Of course, gamma is connected, so sorry, it's quite slow, the sharing of the screen, so is connected. And these two things together just tell me that gamma is a tree. So we call a connected graph with no circuits is called a tree. And then the third property is that every vertex has exactly two neighbors. And we can call this a kind of regularity. So gamma is a regular tree where the valency, so the number of neighbors, is 2. So this is n equal 2. But you can ask for the same properties, but for example, with the number of neighbors 3 or some other integer, natural number. And for example, for n equal to 3, you have a picture like this. If I will be able to draw. So you have a tree which is regular and it's going like this. Okay, my picture is not so nice, but I think that you can imagine how this tree grows. And now let's try to do the same exercises I gave you before for these three here. So just try to think about the possible automorphism that you can have. I'm not asking you to actually prove, but try to think about some possible automorphism and prove that the automorphism group of these three is non-discrete with a compact open topology. And then you can just compare the two cases. And then if you want, you can try to go to some general n greater than 3. And so this is a good exercise with this topology and automorphisms group over 3. Okay, now probably I have to speed up a bit. I was too much relaxed. So I want to lead you to the definition of totally disconnected locally compact groups. So I need to explain you what does it mean to be totally disconnected and to be locally compact. Hopefully these notions are already well known for you, but you are familiar with this notion, but let's go there together. In order to talk about total disconnectedness, I need the notion of identity components, at least for topological groups. So let G be a topological group and define the equivalence relation X and Y are related if and only if there exists a connected subset of G such that X and Y belong to C. Since this is an equivalence relation, we obtain equivalence classes, and these equivalence classes are called connected components of G. But again, we are in the topological group G, so we have a distinguished element, which is the identity. So we look at the equivalence class of the identity, which is called the identity component. And I will denote it by G naught. Another exercise, because I like to ask people to do exercises, is the following. Prove that the identity component is actually a closed normal subgroup of G. This is going to be a very important property for the next part of the talk. A topological group G is said to be, you can see here, there is connected and totally disconnected. Because now we know that the identity component is a closed normal subgroup. So we have two opposite possibilities. We have the identity component can be the whole group, and then the group is going to be connected. Or the identity component is trivial, and then we say that the group is totally disconnected. The totally disconnected case, again, I want you to think that what is happening at identity is happening everywhere else. So this means that if you look at any other element in the group and you look at the connected component containing that element G, then you will find again a singleton. So you just have that the connected components of the whole group are crushed to points. This is not happening only at identity, it's happening everywhere in the group. Okay, now I started the lecture with the definition of topological group with the assumption of Hausdorffness. Now I want to show you that for the groups we are going to talk about, this assumption was not necessary. Let's see, every totally disconnected group is Hausdorff. This is what I want to prove. In order to prove this, I need to recall a property of Hausdorffness that is the following. So a topological space, X tau, is Hausdorff if and only if the diagonal which is this set here, is closed in the product. Okay, so I will prove that a totally disconnected group is Hausdorff by proving that the diagonal is closed. This is what I want to do. Okay, in order to prove that the diagonal is closed, I define a map from G times G in G, so such that the diagonal is going to be the preimage of something. So xy maps to x times y to the minus 1. This is continuous because multiplication and inversion were continuous in G. This means that diagonal of G, which is nothing but the preimage, it's not synchronizing very well. So this is the preimage of the trivial element, but the group is totally disconnected. So actually the trivial element is the connected component G naught, and G naught, this is closed by this exercise here. So we have that the preimage of G naught is closed, and then the diagonal is closed. And this means that the group is Hausdorff. Clearly, you can use the same proof to prove that for topological groups, Hausdorffness is equivalent to the axiom T1. So you just need points to be closed in order to get Hausdorffness. Actually, topological groups are very nice from this point of view, from the point of view of separation axioms, because you can just prove that, I think, T3 and probably T3 and 1/2, they are all equivalent to Hausdorff. So they are all together in the same, they are all the same. Okay. So every totally disconnected group is Hausdorff, so we are happy with that. Then my plan was to prove also that the quotient by the identity component is totally disconnected whenever you start from a group which is not totally disconnected. But I don't have so much time, so I will skip this proof. But this is important for what I'm going to talk about now. So let's keep in mind that if I start from a topological group and I quotient by the closed normal subgroup given by the connected component of the identity, then what I get is again a topological group which is totally disconnected now. But this is not difficult to believe in because you are just crushing connected components to singleton. So you should be happy with this statement without proof. Locally compact groups, the other piece that we need. A topological group is said to be locally compact if the identity has a compact neighborhood. Examples are discrete groups, then compact groups, there is the reals, products, matrices. Then here you have an example of a group which is not locally compact. So if you consider the subgroup of rationals inside R and you use the subspace topology, then this group is not locally compact. Because Q is not closed in R and locally compact subgroup has to be closed. So this is a property that it's well known for locally compact groups. So this one is not a locally compact group. Okay, so for us, totally disconnected locally compact groups now, it should be clear what they are. They are groups such that topological groups in which the identity has a compact neighborhood and a trivial connected component. discrete groups are totally disconnected, locally compact groups. Compact groups are not always totally disconnected. So it depends on this property here, but they are always locally compact. Why I am so interested in this class and why people, mathematicians, are interested in this class. The motivation is the structure theory, one of the motivation, because it's not the only one, but one that I like to propose is the following. So if you start from G, locally compact group, and you consider inside G the connected component, so this is locally compact and connected. As we saw before, I can quotient by this normal subgroup, which is also closed. So I got locally compact and totally disconnected. There is a problem with the PDF. I cannot write totally. Probably it's my connection. Okay, so this means that the structure theory of locally compact groups can be in some sense presented as the, I don't want to say things that are not very correct, but there are two pieces in this theory. So you have the connected part and then the opposite part, which is the totally disconnected one. And at least in theory, since every locally compact group is an extension of a connected group by a totally disconnected piece, at least in theory, you should be able to answer some questions about locally compact groups in general by reducing this question to the connected part, the totally disconnected part, and then combining the answers there in order to get to go back to the arbitrary locally compact group. So TDLC, so totally disconnected locally compact groups, plays a role in the structure of locally compact groups. At the same time, this part here, the connected one, is the part we are happy with, because in the was probably in the end of 90s, there was the famous solution at the Hilbert fifth problem. This was a problem about locally Euclidean topological groups, and Hilbert asked whether it was enough to have something locally Euclidean in order to get something of Lie type, a Lie structure on the group. And the answer is positive, so this is enough, and there is now, we have a positive answer to the Hilbert fifth problem, and this answer brought a characterization of connected locally compact groups has, so connected LC groups are inverse limits of Lie groups. This means that Lie technique can be used to study connected locally compact groups. So this means that our understanding of this part is quite deep. And the part that is still open is the totally disconnected case. So, and I have to say that for years, this, the theory of totally disconnected locally compact groups remains still for many years. And we had some breakthrough in the end of the 90s, and now the progress made with the general theory is huge. And so, yeah, there is hope to be able to, I don't want to say classify because it's not the right word, but to reach a deep understanding of the structure of these groups. But a lot of work is still needed. So this is the motivation. So the motivation, one motivation that I can offer is this one. So we want to study locally compact groups in general because they are ubiquitous. The connected part is, let's say, clear. Let's have a look at what is happening on the totally disconnected part. I want to conclude this lecture with one example of locally compact groups that are in particular totally disconnected. This class of groups is quite famous, so probably you already know it. What is a profinite group? A profinite group is the inverse limit of a surjective system inverse system of finite groups. And this inverse limit is endowed with a subspace topology coming from the product of all the finite groups that are in the inverse system. Here you can see some famous examples of profinite groups. The thing is that since they are closed subspaces of the product of finite groups, profinite groups in particular are compact and totally disconnected. Compact because this is compact by Tikhonov topology, Tikhonov theorem, and totally disconnected because product of totally disconnected thing is still totally disconnected, and subspace of totally disconnected groups spaces are totally disconnected. So profinite groups are compact and totally disconnected. In the next lecture, I will prove one of the main theorem about the theory of totally disconnected locally compact groups. And thanks to this theorem, we will prove that profinite groups are actually the compact case. So they are the compact TDLC groups. So from this thing here, I know that there is this inclusion, but I am going to prove the inclusion in the other. I don't want to do that. On the other side. Why I'm telling this now? Because one thing that you should keep in your mind while you're investigating totally disconnected locally compact groups is that this class is huge. Indeed, they contain all discrete groups, they contain all profinite groups, and they contain various other examples of groups that are very different. So this class is huge. But at the same time, discrete groups and profinite groups are going to play a central role in this theory. So it's quite important to see these classes inside the class of TDLC groups. And you have the discrete piece, the compact piece, and the compact piece coincide with profinite groups. So this is something, an important remark that was needed. Okay, I think that I will stop here for today with this gentle introduction, and that's it. Thank you for the attention.
Thank you.